Hello. I'm going to talk about assembly programming inside of Go, and I'm going to be using the x86-64 architecture for an example. And we're going to do something I pulled from the game engine that I'm writing in Go. As you know, I like writing game engines. I've written fully functional Vulkan game engines in C, also C++, and now in Go. So one of the things that we need to do to make our game engine run faster is to vectorize a lot of our instructions. That is to say, we want to, there's CPUs, so on x86 and 64-bit, x86 64, we have the SIMD instructions, and there's various forms, AVX and all these others, but we'll call them SIMD for now, single instruction, multiple data. On like ARM, we have Neon that we can use, that I've used on Android. But yeah, you essentially take a bunch of instructions, you fire them off all at the same time, and it makes it significantly faster. And I guess we can start with the benchmarks, just so we know how much faster we're talking here. So you can see this is the CPU I ran on here, an i9. This is on a laptop. This is the mobile. I don't know if that is denoted by the H or whatever inside of this schema. But you'll see that I have these ones listed with SIMD, and those are all the ones that have the assembly code to do SIMD instructions. So you can see the difference here on the multiply between a matrix, this is just a regular matrix multiplication, map4 times map4. You can see that we go from 52.5 nanoseconds per operation to 17.47. So that's quite significant, but it's even larger on these when we look at multiplying against vector force. We go from 45 and 44 respectively to 6 and 3. And that's, the difference between 44 nanoseconds per operation and 3 nanoseconds per operation is self-evident. And you can see that in the numbers here on how many operations ran. So this is quite a significant gain for this. And we need numbers like this to do, a lot of matrix multiplication for a game engine written inside of Go using Vulkan. So this code here is essentially what you're taking. You're taking this standard classic map4 matrix multiplication where this is just a very simplistic multiply of this is what you learn in primary school. When you multiply two matrices against each other, and this is using a float 32, so ignore some of the semantics. But that's all that is. It's just taking in two matrices and multiplying them together to get a result. And this is, for example, matrix 4 multiplied by vec4. I don't have a vec4 multiplied by matrix 4, but you get the gist here, where we grab the columns in this case and do just straightforward multiplication. So, of course, these are just straightforward primary school, like what you learn to do by hand. And we're going to convert that over to assembly code. So in Go, if you don't know, you can write assembly code per architecture. So you see that I have AMD 64 listed here as my Go build operation. And this is just to limit it. So when I do, say, Android with Neon, I would have its own set of instructions to do the Neon instructions. In this particular case, we can do, I think it's 256-bit operations. And in Neon, it's up to 128. So it's a difference of 8 floats or 4 doubles versus, 4 floats and 4 doubles and 2 floats, something like that. But that's semantics of the platform. So these are 2 helper macros that I've set up. I've set up a dot product, where we can take in the matrices we're interested in, or the matrix. I guess vectors are matrices. So we can take in those 4 vec4s and place them into a third vec4 basically. And we're just going to use these UPS instructions. I think this is packed sign. That's what the PS stands for. So we're doing, or packed single, my bad. So we're doing these packed single operations because we're operating on float 32s in this case. So this is just a dot product. It's very simple. We're taking A and we're moving it to X0. We're using the X registers because these are the XMMs. If you're familiar with x64 assembly programming, Go has its own special sauce, its own special sauce assembly language, which tries to combine a lot of the commonalities between architectures, and so it uses just X0 here, like X0, X1, X2, etc. So that's essentially what we're doing. We're taking the A and the B, and so we're doing a multiply against those two here, and then a horizontal add. That's what the H is for, and we're horizontally adding, and then we're moving it from the X0 register to the 2. So this is just a simple dot product using these vectorized operations. And then we have this helper function because we need the ability to pack the matrices, because the matrices you can think of as four vec4s. They're I'm pretty sure you're familiar if you're watching this, but you got a vec4 essentially. You can choose which way you want to do it, left or right or whatever. But you have four numbers, and then four numbers, and four numbers, and then four numbers. So either way that you slice this vertically or horizontally, you've essentially got a vec4 and these matrices. So this is just taking those matrices and it's packing them, as it says, pack columns. It's packing the matrices using this insert PS. So insert packed single. So we're telling it where to insert it. So this is, I believe, it's been a while since I programmed this. I just kind of want to go over it. This is essentially where the flags telling us where we want to pack it. So you see these first four have the same flags. The next four have the same flags. The next four have the same flags. And the next four have the same flags. So essentially you can see we're going through the registers and we're pulling out. So this mask, we'll talk about it a little bit more in a bit, but this mask is essentially doing a mask against the argument here to figure out what float to pack. And that's kind of, I've used this comment to denote which float we are packing, but that's what we're doing. We're going through and we're packing each one of these floats into this. And then for the usage, we have, let's go to the simplest one that doesn't use packed columns first. We're going to look at when we multiply a vector 4 by a matrix 4 by 4. You'll notice that we have our comment here saying what the function signature looks like inside of Go. We've got our vec4 as our first argument, and our matrix 4 by 4 as our second argument. And you'll see A and B there. This is where that B comes from when we're looking at the pack columns function. And we see no split. This is telling Go not to split the stack. This is a known function with, we're not creating memory or anything. We're just operating on the arguments we have. So no split is an optimization, or could even be a requirement. So that we say not to split the stack. And then we're saying how many bytes we're going to need for this particular operation. 96 because we're dealing with a 64, a 4x4 float matrix and a vec4, and you add those up and you can get that 96 bytes from that. So in this one we have move the packed sign. So these are the SIMD instructions, and we have our B as our argument here, this B. So we're saying B plus 16 off the frame pointer. So the frame pointer is the stack frame for when we enter this function, and that's going to have access to our stack. So we're saying from the frame pointer, we're going to take B so we're taking B and then we're going 16 bytes off the frame pointer, and we're packing that into X1. So then we have X2, X3, X4. So those are getting moved into a packed single. Did I say sign again? Single. So we've packed in those floats from our stack, and now we're going to run our macro, which is the dot operation on it. So we're going to dot A, which is our vec4. And so we're dotting our A on all of these. So this is just our vec4, 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 vec4. For A, we're just basically passing in A as the first arg. Then we're passing in our X1, X2, X3, X4. They're packed, our packed data. And then we are going to, you'll notice that I use this RET here. And this is to denote the return. So we are returning a value. Oh yeah, I'm pretty sure this 96 also includes the return. So we are returning a value. And so what we're doing is if you remember that dot function or macro we had here, our third argument is our 2. So where are we taking this and setting its value or setting its data? So we're just putting that in the return, and notice we have an offset of 80, 84, 82, 88, and 96. But you can imagine, I think this is basically like a placebo. We're saying store it in 80 bytes from the offset of the frame pointer, and then 84 because 4 bytes make up a float. So 80, 84, 88, and 92, and that's essentially what it is. You can just ignore the return and just think that it's going straight into the frame pointer, which is the return. This is going to be the return vec4 that we have here from this function, and that's essentially what we're doing in this. So this is the simplest form of us packing that in and returning it, and we're just using the macro to greatly simplify our code here. The next one up is a mat4 multiplied by vec4, and so, if you remember your linear algebra days, you know that if a vec4 comes first versus mat4, when you change the order of matrix multiplication, you get a different output. It's not commutative like standard multiplication, unless you're doing things like identity matrices or whatever. So same thing, we have no split. We have the same return because we are returning a vec4 still in this case, as you can see here. So same amount of bytes that are needed. But this one is going to do the pack columns against 0. Remember, pack columns takes B here, and this is our start. So our start offset. And then we're going to take A, which is going to be our matrix 4x4. And we're going to take A and we're going to add 64 to the frame pointer, so A plus 64 on all of these. And we have X1, X2, X3, and X4. Remember, those are packed instead of the packed columns. When we look over here, see where X1, 2, 3, and 4 are where the packing is going. So after we do the packed columns, the X1, X2, X3, and X4 are going to be assigned. And so that's the value we're going to pass in to the dot product for B in this case. And then we're going to do that same return. And notice it's the same exact order, 80, 84, 88, and 92 for those. Okay, so now to come back for the confusing part. So remember that these letters, this A, this B, and this return, are all placebo. They don't mean anything. What actually matters is what you do to this frame pointer. So let's go back to pack columns and let's take a look at what we were doing here. Notice that we said B plus start. Well, the reason we say B plus start is because we're telling, I believe the Go assembler gets mad if you don't put a variable. And so we put in B in here. This could have been A. This could have been A or B. It doesn't matter in either case. So to simplify what I was saying earlier, I said we're passing b, which is our vec4 in here, but we're actually what's actually happening is a is being operated on, because look, a is the first argument here. So frame pointer 0 through 64 is going to be all this matrix. So even though we have a b here, you can ignore it. In fact, I would say just act as if it's not even there, because the reason it's there is to make the compiler happy, which kind of is confusing with the macro stuff. Maybe I could leave it off, I'm not sure. But imagine it's not there now. So now all we're doing is we're operating off of start 0, or start plus 0 from the frame pointer. So let's take one more look. 0 is going to be the first float in this map4. And notice we're passing 0 in for our start. So here, it's 0 plus 0 is 0. So we're actually accessing that first matrix here and packing that into the X. So for those of you who caught it earlier and thought that something was going on with this dot product because I was multiplying in the wrong order, you would have been correct, just because that B throws it off. Now I want to talk about that B one more time that's inside of the pack columns, just because I know it was confusing. The reason it's B is because of this one. Notice it says 64, and this is going to be 0 through 63, and this is going to be 64 through 127, right? So that this macro was actually created for this function, and that's why that B is in there, is because I was actually operating on B. But like I said, don't read through assembly code on Go and assume that the variable here matches the argument. That's critical. If you're looking through people's code, you'll see that all the time. The only thing that matters, I'll reiterate it because of how important it is that offset to the frame pointer. I guess technically also the start. The offset to the frame pointer is the only thing that matters. The variable, just ignore it. Just pretend like it's not even there. So we've taken our dot product here against here's our packed matrix, and notice that I'm using A here, which is doubly confusing. Honestly, I should have put B here. Like I said, imagine that this isn't even here, because all that matters is that offset. So sorry for the confusion. When I coded this, I moved around the macros and didn't think about what it looked like, just because it works. And so I'm probably going to go in and clean that up for the repository. It is a public repository, so it would make sense to make it clear for people. So with all of that mess out of the way, we can talk about the matrix by matrix multiplication. So this is actually taking that map4, and because of this 64-byte offset, and packing it into x1, x2, x3, and x4. So you can imagine that B is equal to x1 through x4 now, and then this is accurately labeled as A here, even though it doesn't matter, because you'll notice it's A plus 0, A plus 0, A plus 0, A plus 0 on these this first 4 dots, 16, 16, 16, 13, etc. Another reason why this is faster, not only from the vectorization, is because notice we have a 4, 4, 4 in here, and the compiler can unroll that because I'm using constants, so it can figure out the unrolling to make that faster. But we are essentially manually unrolling here. There's no branching going on, so we're just manually unrolling it, and that's why there's so much of it. So of course we have our A matrix here in the first column, we have our B matrix here in the X's, and then we have our return, and notice that we're starting at 128 as our offset because A through B is 0 through 127. So our return matrix is going to start at 128 and go up to 192. So that's where all that is. And you can see here what we're doing. We're getting the value for x0 is y0, x0, y1, etc., etc. So hopefully that made some sense. I know assembly is a little bit of a difficult subject, especially for a high-level language like Go, but if you haven't messed with assembly before, Go is a wonderful place to start because it's very easy. You just make a .s file or a .asm. I think it supports both of those files extensions, and then you can just paste this stuff in and just start working with it immediately. You do have to pre-declare. So you see this func here. You do have to basically copy and paste this into a Go file, and then say that I think you say like Go, and then no escape, above your function, and it's pretty much good to go. The only other thing is you'll want to make sure that Go file that you put this in, you put Go no escape, and then you just paste this underneath it. You'll just want to make sure that this is set to build only for the platform that supports these instructions. These these are the I think they're AVX instructions. So you wouldn't do this on ARM, for example. If you were doing Neon, you'd build a special assembly just for that. So one of the downsides, obviously, for assembly, why we don't code in it, typically these days is just cross-platform languages, so we don't have to write two versions of our code. There are some high-level assembly projects and stuff out there, though, that are kind of fun to use. So now I think I've talked about pretty much everything here. There is one thing which I know I want to talk about because it is very confusing, is this insert PS. The insert PS is confusing because of these flags, because you're essentially flagging how you want to accept the floats out of this memory. Because notice you're taking in 4 floats here. You need to tell it which float you're trying to access. So notice that we have 0, 4, 8, and 12 here. So you can see I'm skipping by those 4 bytes in the matrix. So that's important because these all use the same flags. So first of all, when you have a $14, this is the decimal value 14. In other assembly languages, the dollar could denote hexadecimal. But we're dealing with, if we wanted hexadecimal, it would be $0x14. So we're actually dealing with decimal. So let's figure out what they each are. So if we looked at the bit pattern for 14, we would get 1110, right? And we're just talking about these 4 bits. And this number here is an 8-bit immediate value. So we're dealing with, actually this has 4 leading zeros, so I guess let's just do 0, 0, 0, 0, and then 1, 1, 1, 0, right? And then our next value is going to be 16, so we're going to have, let's do 16, 32, and 48. And I'll just line them up over here. So 16 is going to be 0, 0, 0, 1, 0, 0, 0, 0. And then we're going to have 32, which is going to be 0, 0, 1, 0, 0, 0, 0, 0. And then we're going to have 48, which you'll see the pattern here. You're still going to have zeros at the end. We're going to have 0, 0, and then we're going to have 1, 1, 1, 1, 0, 0, 0, 0. So what do these mean? Well, we can break these 8 bits up into 3 sections. One section of 2 bytes, another section of 2 bytes, or bits, sorry, and then one more section. And that section is going to have the remaining 4 bits. So this is the left-hand side is the source. This middle one is going to be the destination. And this last one is the 0. And it's a mask. So notice all of the last ones here, 16, 32, 48. they all have zeros in the end. If there's a 1 in this in one of these bits, then it's going to set the corresponding value to 0. It's basically going to zero it out. And you can imagine that we're packing 4 floats in here. Notice 1, 2, 3, 4. We're packing 0, 0, 0, 1, 0, 2, and 0, 3. So when we have something like in this first case, 1, 1, 1, 1, 1, 1, or sorry, 1, 1, 1, 0, we're setting these 3 bytes, or these 3 floats here, these packed ones, to 0, and we're not setting the last one. Now let's look at what we do here, 0, 0, 0, 0. So if we have 0, 0, 0, 0, notice that with 2 bits you can have 4, you can have 0, you have 1, and you can have 2, and you can have 3. 0, 1, 2, 3. So you got 4 different values or indices, which match up to the 4 floats. So you can imagine we have float, 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 right? So if this is 0, 0, we're talking about the first float. And I'm going to go right to left. I believe that's the order it goes in. Yeah, well, I think the order is right to left. So we have 0, 0 here is the source and then the destination. So we can say that these 4 floats are the from, or let's see if there's a better way for us to kind of view this. So let's imagine we had some floats, and we're going to keep it simple. We're not going to do 1 dot whatever. We're just going to do 1, 2, 3, 4. So if we took this idea and let's make 4 floats, we'll have, there we go. We got 4 floats. We've got, this is going to be we'll make this the we'll make this the source and the next one the destination. So here's 4 more. Right? So let's say that the source is 1, 2, 3, 4, and the destination is 9, 8, 7, 6, right? So right now we're saying select 0, 0 from the source. So we're going to select this guy here, this 4. And then we're going to say select 0, 0 from the destination here. So this gets copied into that location. Now notice our bit mask, 1, 1, 1, 0. Anywhere we see a 1 turns to, sets the destination to 0. And that would be these 3 here. So our result is going to be, if we have our boxes here, it's going to be 0, 0, 0, and then 4 because we copied the 4 in. Now let's try another one here. Let's say that we're doing, let's say we're doing 32 here, right? So that's 0, 0, 1, 0, and then a bunch of zeros. So 0, 0, 1, 0, and then a bunch of zeros, right? In that case. So let's take this same exact one. And so what is the source going to be? The source is going to be 4 again because it's 0, 0 in this case. And then our destination here is going to be 1, 0. So let's take this, sorry, if 1, 0. So this is going to be 2. So 0 in the 1's place, 1 in the 2's place. That's 2 plus 0 is 2. So we're going to say 0, 1, 2. So 8 is going to be our target. So in this case, it's going to be, I feel sorry for anyone skipping ahead because these boxes are just going to be all over the place. So in this case, we're going to leave what's in the destination. And we're going to imagine that we didn't do this zeroing out before. This is its own isolated instance. So we have nothing in the zeros place. We're not zeroing anything out because if you look at the 32, we have 0, 0, 1, 0, and then a bunch of zeros. So we're not zeroing out any of the fields. So this is actually going to be, we're going to keep the 9. We're going to copy the 4. The 4 is going to get copied into that second index there. So 9, 4, 7, 6 in that case. So this is a little, This is a little weird, but there is a method to the madness. You only have 4 bytes, so you only need 2 bits to describe where you're coming from and where you're going. And then the zeroing is important because notice that we use it here in the beginning, up here, to zero out the X register. Notice we have a different X register. We have X1, X2, X3, X4. So we're zeroing out, since we're doing 14, 14, 14, 14, and we have these zeroing outs here, we are zeroing out X1, X2, X3, X4. We're just clearing them as we are packing the values in there. So we're doing dual work on these first 4. We're both clearing out X1 through 4, and we are assigning the first byte in. The first float in. And then these next ones, it's in the same order. 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. Next ones are just copying. We're just now copying each one. And notice that the this frame pointer offset, notice 0, 4, 8, 12. And then we got 16, 20, 24, 28, 32, 36, 48. So this is just doing that insertion of the matrix, and we're putting in that, I think the column major order is the word for it. Notice it's pack columns, not pack rows. So we're packing the columns so that they're prepared for multiplication. So sorry about that one. That one's a little bit more complicated of an instruction. I mean, moving a pack single is pretty straightforward. You're just taking a value and moving it into a register. Multiply is pretty obvious. You're just multiplying. Horizontal add, you're just adding the floats and the registers together horizontally. So all of these instructions really just make sense. The insert PS is the one that gets you. So yeah, that's the assembly code. If you want to check out the assembly code, I'll put a link in the video where you can check out the GitHub repository. I'll just put a link straight to this assembly code file so you can check it out. But yeah, if you have any questions, let me know. But yeah, that's how you do assembly programming in Go. And I had a lot of fun with this, and you can do obviously more than just vectorization. If you want to speed up your code, dropping down to assembly and doing very specific things for your current platform is a great way to do it. So if you have any questions, let me know. Sorry if some of this got a little hairy. Assembly is hard not to get hairy because certain things are cryptic. Cool.